Okay, so two new rules on derivatives. The derivative of a basic log with a base of a, and the derivative of an exponential function with a base of a follows each of these rules. So for this one, the derivative would be 1 over the natural log of the base, a, times whatever u is in the denominator as well, times the derivative of u, and that's really just the application of the chain rule. Over here, it's the natural log of your base times the exponential function itself times the derivative of what's inside of the exponent, which again is the application of the chain rule. So the one log function that we do already know the derivative of is the natural log, and we just knew that that was 1 over x. But it is still a log function, so if we follow this rule, natural log is essentially log base e of x. So if we're applying our derivative rule, it's going to be 1 over the natural log of a. A comes from the base, so the base here is e, times whatever's in the u position. So in the u position, that's what we're taking the log of. That's x in this case, times the derivative of whatever's in the u position. So the derivative of x would just be 1. So that would be doing this natural log derivative via the log rule. Obviously what happens is the natural log of e just cancels, and this ends up just boiling down to 1 over x, which is what we memorized earlier this chapter. For the exponential one, kind of a similar thing. It's the only exponential one we have looked at so far is this e to the x power. So if I kind of treat the e as my a and the x as my u and follow the rule here, the natural log of a, and in my a position is e, times whatever's in the base position, e to the x power, so you just kind of take this for what it is, times the derivative of the exponent, so the derivative of x is 1. So again, what happens here is the natural log of e just cancels, and this just ends up being e to the x. Most times, if the base is anything other than e, that's not just going to cancel out like that. So we started with these because these were pretty quick and easy rules, but they really are following a longer, more complex rule in basic logs and basic exponentials. So let's just jump right into this with example number 1, which is an exponential function. So we're following this rule. So g prime of x equals. So it's always going to start with the natural log of your base, which is 5, times the exponential function taken as is, so 5 to the negative x power, times the derivative of what's inside, which would just be negative 1. That's your chain rule. So when this gets cleaned up, it's just negative natural log of 5 times 5 to the negative x power. Things can get more complicated, obviously, because you're going to have to follow these rules within a quotient. So f prime of t is your bottom, times the derivative of the top. Now the top is an exponential function, so that's going to be the natural log of your base, 3, times the function taken as is, 3 to the 2t, times the derivative of what's inside of that exponent, 2. So that's the bottom times the derivative of the top, minus the top, 3 to the 2t, times the derivative of the bottom, which is just 1. So in simplifying this, we have a 2t times 3 to the 2t. Unfortunately, we cannot multiply the 3 times 2 and make 6, because that 3 has its own exponent, ln of 3 minus 3 to the 2t power. So this is just a binomial, and both terms of the binomial have 3 to the 2t, so I would not be surprised to see them factor out the 3 to the 2t. And you're left with 2t ln of 3 minus 1. I forgot all over bottom squared. bottom times derivative of the top minus top times derivative of the bottom all over bottom squared, all over bottom squared, all over t squared. Sorry about that. Okay, if we jump to the log one here, I'm going to zoom out so I can see the rules on the piece of paper at the same time as the problem. So, h prime of x equals, always starts with 1 over the natural log of a. A is your base, so the natural log of 3. Times u as is. Now u as is this whole thing here, which is pretty crazy. Times the derivative of u. So we now need to multiply by the derivative of u. So I'm going to treat that u momentarily as just x over 2, I think, or 1/2 x root x minus 1. That'll allow me to do the product rule, which I like. So first times derivative of the second. If you're following a chain rule here, you would technically be multiplying by 1. So it doesn't change much. So first times derivative of the second plus the second times the derivative of the first, which would just be 1/2. Okay, so if I'm cleaning this up, I'm going to, I'll keep this the same for now. Focus on that second piece. So this will be, this is 1/2 x, so that x is technically going to be on the numerator still, over the 2 times the 2, we put a 4 in the denominator, and then root x minus 1, plus root x minus 1 over 2. So I am going to touch upon this denominator right now because it has a fraction within the denominator. So really, again, the 1 over that will just flip it. So it's 1 over the natural log of 3, and then this is going to get flipped to 2 over x root x minus 1. So there's this times our binomial. And again, this can now be rewritten as a single fraction. So 2 over x natural log of 3 root x minus 1 times this binomial. And then I would distribute. So taking this times that will give me a numerator of 2x. Well, that x will cancel with that one. So 2 over natural log of 3 to 4, so 4 natural log of 3, and then the root x minus 1 times the root x minus 1 will just be x minus 1. Plus, on my second distribution, this x minus 1 is going to cancel with that one. This 2 is going to cancel with that one, so it's just going to be 1 over x natural log of 3, and that would be it. They both have a natural log of 3. We could get a common denominator and combine these. I'll do it just for the sake of if we have to. So this one needs a 4. They both have the ln of 3 already. This one has an x minus 1. This one would need an x minus 1. This one has an x. This one would need an x. So up top we would have 2x distributing a 4, so plus 4x minus 4 all over your common denominator. X, 4x, natural log of 3, x minus 1. Okay, so this 6x minus 4 over 4x natural log of 3, x minus 1. If you wanted to, again, there's a 2 that could be factored out of this and a 2 factor down here. So we could make this 2 times 3x minus 2, and this 2 and this 4 would reduce. So this will be at the final answer I can come up with. 2x natural log of 3, x minus 1. Flip to the back. What I'm going to do, just so it's all on the same paper and I'm not going to go back and forth, is I'm going to copy down the derivative of a log rule. So d dx of log base A of u is 1 over the natural log of A times u prime. Okay, so we'll use that for here. Y prime equals 1 over the natural log of our base 10 times u as is, x squared minus 1 over x, times the derivative of u. So that's a quotient rule. Bottom times derivative of the top minus top times the derivative of the bottom is just a 1 all over bottom squared. So in my first fraction, this is going to get flipped because it's 1 over it. So the x is going to come up to the numerator, and the denominator is going to be the natural log of 10 with the x squared minus 1. Up here, we're going to have a 2x squared minus an x squared minus a negative 1 is going to be a plus 1. I'm pretty much ignoring that 1. So that would be 2x squared minus x squared, which is x squared plus 1 over x squared. And if I'm multiplying these two together, this x will cancel with one of those. So I have my final answer. X squared plus 1 up top, x, natural log of 10, and x squared minus 1 on the bottom. And our last one here, which is a log function again, so I'm going to be referencing this. First things first, this is a product rule. First, second. So we're going to apply that. So first times the derivative of the second, and we're going to get pretty lost in the derivative of the second, plus the second times the derivative of the first is going to be 3/2 t to the 1/2. The big guts of this is in this one right here. So to take the derivative of a log, 1 over the natural log of 2 times root t plus 1 times the derivative of that. Now that is t plus 1 to the 1/2 power. So the derivative of that would be 1/2 out in front, t plus 1 to the negative 1/2 power, times the derivative of what's inside of that, which would just be a 1. So we don't have to worry about that. I'll open up my parentheses. So if I'm cleaning up in here first, leave my t to the 3/2 alone. Up top is just going to be a 1. In the bottom, I'm going to have 2 ln of 2, and then a root t plus 1 times a root t plus 1. Because this is moving down into the denominator as a root t plus 1. Times the root t plus 1 that's already there. We're looking at just t plus 1, which is nice. Plus, if we want to make a fraction out of this, 3 will be up top. Root t will be up top. Log base 2 of root t plus 1 will be up top, and the only thing in the denominator will be the 2. If we want to get all things radicals, this would go up top here as just the square root of t cubed. Which then we can make t root t over 2 ln of 2, t plus 1, plus 3 root t log base 2 of root t plus 1 all over 2. So, again, if you wanted to get a common denominator, you could give this one a natural log of 2 and a t plus 1, and then go from there. But I'm good with this as is. Your homework is just this page 170, 5 or 6 problems of this. I will tell you this to help. I will not make you memorize these. I will give you these 2 derivative formulas, so don't worry about memorizing them, just have them near to you. And your homework here, due tomorrow. And once we're done with this lesson, we're pretty much done with the new messy derivative rules, and then we'll just move forward with applications that will hopefully lighten the load.